Hey everyone, welcome to This Explainer. Today, we're completely stripping away the hype to see exactly how physical AI is operating in the real world right now. Forget those CGI science fiction movies and those perfectly edited laboratory demos. We're looking at the hard, concrete data and the actual real-life factory floors where this tech is literally already deployed. Right, let's dive right in with a question that honestly sounds like it belongs way in the distant future. But as of 2026, it's actually an audited reality. Are humanoid robots already building your car? Well, the short answer is absolutely yes. And the long answer? It's a seriously fascinating study in modern engineering and logistics. So here's what we're going to cover today. 1. The factory floor reality. 2. Hardware, legs versus wheels. 3. Brains, sensors, and compute. 4. Scaling autonomy in logistics. 5. The Tesla Optimus contrast. And finally, 6. Co-working with physical AI. Let's get to it. Section 1. The factory floor reality. To really wrap our heads around what's happening out there, we first need to define physical AI. Basically, it's the convergence of artificial intelligence and robotics right down at the level of the factory floor. Think of it as the physical layer of digital production. BMW has absolutely championed this concept. With deployments at their Spartanburg plant in the US and the Leipzig plant in Germany, they're taking AI out of the cloud, giving it a physical body, and putting it to work doing the heavy lifting. Just think about this number for a second. 1,200,000. That's not a simulation. That represents the actual number of steps a robot known as the Figure 02 logged during an audited 11-month deployment at BMW's Spartanburg plant. I mean, that is just an incredible volume of movement. It's a huge testament to the kind of real-world durability they're achieving outside the lab. And the results of all those steps are pretty phenomenal. Again, this wasn't a lab demo. These robots worked actual 10-hour shifts, 5 days a week. They handled repetitive, high-precision kitting and assembly tasks. We're talking 90,000 sheet metal parts moved, 1,250 operating hours logged, and contributing to the production of 30,000 BMW X3 vehicles. And they did all this while exceeding a 99% placement accuracy. That is verified, third-party audited industrial throughput. Section 2, hardware, legs versus wheels. So it turns out not all physical AI looks the same. We're seeing this really fascinating divergence in how these machines actually get around the factory. On one hand, you have Figure AI's human-scale bipedal design, like the Figure 03. It's wrapped in a soft textile cover and optimized for navigating spaces built for humans. On the totally opposite end, you've got Hexagon Robotics Aeon. Aeon uses wheeled legs for hyper-fast mobility. We're talking up to 2.5 meters per second. It's built explicitly for the factory floor, specifically targeting high-voltage battery assembly at BMW Leipzig. Arnaud Robert from Hexagon actually summed up their whole industrial vibe perfectly, saying, "We're not in the dancing business, we're in the working business." Now, for the robots that do need to handle delicate or weirdly shaped objects, dexterity is literally everything. Think about the number 3 here. Figure 03 uses these custom electromechanical actuators and incredibly advanced fingertips that can detect forces as tiny as 3 grams. Let me put that in perspective. That's sensitive enough for a massive robot to feel the weight of a single paperclip resting on its finger. That's wild. This sub-gram feedback is an absolute game changer. It allows Figure's AI, which they call Helix, to actually predict if its grip is going to slip and dynamically adjust its force on the fly. When you compare that to traditional, rigid mechanical arms that kind of just clamp down blindly, this means the robot can safely handle fragile, irregular, or even moving assembly parts without just crushing them to pieces. Section 3. Brains, sensors, and compute. Okay, having a great robotic body is cool, but it means absolutely nothing without the right brain. Figure manages the incredibly hard jump from simulation training to actual industrial deployment by dividing their control architecture into 3 totally distinct timescales. Think of it like this. System 2 is the semantic brain, processing speech and reasoning slowly. Then System 1 acts fast, translating those commands to precise joint movements. Finally, System 0 operates at lightning speed, 1 kilohertz, managing dynamic balance and torque. It's actually designed to mimic human biology, blending conscious thought with automatic reflexes. Now, we have to talk about a massive debate in the industry right now. How do these robots actually perceive the world? Figure goes all in on what's called sensor fusion. They combine head cameras quite literally embedded in their palms to see around visual blockages, and tactile sensors, processing the whole shebang entirely on embedded onboard GPUs. Tesla, on the other hand, uses a vision-only approach. They pulled this straight from their full self-driving automotive software stack. They rely strictly on 8 cameras, constructing a 3D vector space via their custom AI Fi chip, totally ditching active ranging sensors like LiDAR. It's a huge, fundamental split in engineering philosophy. Section 4. Scaling autonomy in logistics. So these platforms are now transitioning beyond the strict confines of automotive assembly lines and expanding their reach. Figure is currently tackling the multi-brand chaos of distribution warehouses. They've partnered with Catalyst Brands to deploy robots at a massive logistics center in Reno, Nevada. Out there, these robots are servicing diverse brand portfolios, places like JCPenney and Aeropostale, and automating really physically demanding supply chain tasks like Joey pouch induction sorting. What this partnership proves is that physical AI can absolutely scale as a flexible solution that adapts instantly to dynamic retail environments. But how do they keep getting smarter? Well, Figure uses a blazing fast 10 gigabit per second wireless data link, while the robots take breaks on 2 kilowatt inductive charging pads. During these breaks, they are continuously uploading terabytes of raw visual, tactile, and operational data straight from the warehouse floor. They use this massive real-world feedback loop to actively improve the AI performance across their entire fleet at the exact same time. Section 5. The Tesla Optimus Contrast. So how do all these verified commercial deployments stack up against arguably the most famous robot on the internet? Well, there is a pretty stark contrast right now. Figure AI and Hexagon's Aeon both have third-party audited enterprise success at BMW and Catalyst Brands. But when we look at Tesla's Optimus Gen 2 and Gen 3, their deployment is strictly in-house at Tesla's Fremont and Austin facilities. Their status, still firmly internal testing only. Even Elon Musk mentioned on a 2026 earnings call that their units are primarily for learning and data collection right now, rather than knocking out productive tasks at commercial speeds. That being said, you absolutely cannot discount Tesla's engineering scale. Just look at the specs for the Optimus Gen 3 hands. We're talking 22 degrees of freedom per hand, driven by 50 servo actuators. Interestingly, Tesla placed all those hand actuators up in the forearm, using biomimetic tendon-driven mechanics to keep the hands lightweight. This setup allows for over 3,000 discrete manipulations. So Tesla's massive compute power and their ability to rapidly scale actuator volume gives them a really huge potential advantage for future mass production, even if they're still testing internally today. To train these highly complex hands, Tesla relies really heavily on human teleoperated video data inside their Fremont factory. Basically, human workers perform the tasks, the video trains Optimus through imitation learning, and that feeds this massive neural loop that updates the whole fleet over the air. But right now, commercial competitors hold the clear advantage because their robots are actively generating verified industrial output for paying clients, while Tesla is still heavily focused on gathering data inside its own walls. Section 6. Co-working with physical AI. So what does this massive technological shift actually mean for human workers like us? Milan Nedeljkovic, the incoming CEO of BMW, really hits the nail on the head here. He says this symbiosis of engineering expertise and artificial intelligence opens entirely new opportunities. And that's exactly what BMW's pilot programs have shown. Successful physical AI integration is entirely about complementing human labor, not replacing it. What we're really looking at is a brand new division of labor. Humanoid robots are literally built to take over those physically demanding, highly repetitive assembly tasks that cause strain and injuries. The heavy lifting, the dangerous sheet metal kitting, the stuff that simply wears people down. By eliminating those hazardous tasks, it elevates the human workers. It frees us up to manage the AI, oversee the complex quality control systems, and handle the high-level process management that, frankly, robots just can't do. We've clearly seen that the transition from science fiction movies to factory floor reality has already happened. From Figure logging over 1 million steps at BMW to Aeon zipping across the floor on wheels, the future of manufacturing is literally already walking or rolling around the factory floor today. So I'll leave you with this one vital question. As this tech scales, how are you going to utilize a physical AI coworker in your operations? Thanks so much for joining me for this explainer. I hope it brought some clear perspective to an incredibly fast-moving space.